In the next few lectures, we are going to study the properties of vector fields. Our goal is the Frobenius theorem. Given a vector subbundle of the tangent bundle of dimension k, we are interested in knowing whether or not this subbundle is integrable. In other words, whether there exists a partition of our manifold in inverse submanifolds of dimension k such that the tangent space of any of these submanifolds at any point is actually given by the fiber of our subbundle. In order to make the statement and then show the Frobenius theorem, we need to introduce the Lie bracket of two vector fields, and we are going to study the geometric properties of the Lie bracket. But in order to define the Lie bracket, it is interesting to provide a definition that it is independent on any choice of local coordinates. And so, in order to give this definition, we are going to identify the space of C-infinity vector fields with the space of derivations of C-infinity functions. And we'll see in the next lecture that this identification makes the definition of the Lie bracket extremely simple. Moreover, in order to get there, we are going to see first an identification between the tangent space of a manifold at a point and the derivations of the space of germs at that point. Okay, so that's our goal for today: identifying tangent vectors and then vector fields with derivations. The goal of this lecture is relating vector fields and derivations. Okay, so let us introduce the setting. We are going to consider first a manifold M, a manifold without boundary, and a point of the manifold, a point X. Now we consider the R algebra of C-infinity functions defined in a neighborhood, an open neighborhood of the fixed point X in M. Okay? We're going to define an equivalence relation in that set of functions, which is that two functions that can be defined in different open neighborhoods of the point X are indeed related if there exists a neighborhood W of X contained in the intersection of the domains of definition such that the restriction of these two functions to W are equal. Okay? So the idea is that two functions are identified when they are equal in a neighborhood of the point X. The set of classes is going to be also an R algebra that we are going to denote like this, okay? And it is called the space of germs of C-infinity functions at the point X, okay? We consider functions that are defined in an open neighborhood of X, and then we identify two of them if they are equal in a neighborhood of the point X, okay? We denote by, we use this notation for the class of F, and here this F index to make clear that we are working in the space of germs at X. We use this notation for the class of F in the space of germs at X. It's like that. And now we want to understand, to interpret the tangent space of the manifold M at the point X as a set of derivations. So let us consider a tangent vector U at the point X and then a germ of function F. And we're going to consider a C-infinity curve gamma defined in a neighborhood of 0 in the line such that the value of the curve at 0 is the point X, the curve is passing through the point X at 0, and the derivative of gamma at 0 is the tangent vector U, where the derivative is just the differential of gamma at the point 0 applied to 1. So in this situation, we are going to define the value of, we're going to apply U to germs of functions by using this formula. U applied to the germ of F is just the derivative of the composition of gamma and f with respect to t at the point 0. This is well defined, and indeed it does not depend on the choice of gamma, okay, because of the chain rule. And it does not depend on the choice of a representative either, because in order to know this derivative, we just need to know what happens in a neighborhood of the point x. So because of that, it does not depend neither on gamma nor on the representative that we are choosing. Okay, something that it is interesting is that if we consider a C-infinity vector field, okay, and the value of this vector field at the point x is equal to u, then the result of applying u to the germ of f at the point x is equal to the derivative of the composition of f and phi t. Here it's something is missing, phi t of x at the point t equals 0, where phi t is just the d-time flaw of the vector field. This is because when we fix x and we make this expression to depend on t, when we vary t, this is a curve such that the point t equals 0 is equal to x, and such that the derivative of this expression with respect to t is the tangent vector u. So it's essentially this definition. But something that it is interesting is that this expression over here is an expression that is independent on the choice of coordinates. And so this definition over here is also going to be independent on the choice of particular coordinates that we consider, okay? It's something that we can define for any manifold. Our map U is R-linear. This is very simple. It's because the derivative of a sum is the sum of the derivatives, and the derivative of the product of a function and a real number is the real number times the derivative of the function. And moreover, what we have is that since this composition is a real function of an interval of the real line, we're going to have that the derivative of a product is going to be the derivative of the first function times the value of the second function at the point x, which is well defined. It's the same, of course, for all the functions that define the same germ, plus the value of the first function at x times the value of u applied to the germ of g at the point x. So this is the Leibniz rule, okay? And because of these two properties, then our tangent vector defines a derivation of the space of germs at the point x. Indeed, almost by definition, as we can see here. Given a map from the space of germs at the point x to R, we say that it is a derivation of the space of germs if first D is R-linear, and then it satisfies the Leibniz rule for any choice of germs F and G at the point X. Since these two properties hold, because of the results in the previous slide, then every tangent vector defines a derivation of the space. Every tangent vector at the point X defines a derivation of the space of germs at X. Okay, so we have this map over here, and we are going to study the properties of such a map. Okay, this map, which is a map between vector spaces, is indeed an isomorphism of vector spaces. So in particular, every derivation is obtained by considering a tangent vector. Okay, first of all, we are going to see some interesting properties. The first one is that if we have actually a derivation of the space of germs at the point x, then the derivation applied to the germ of the constant function equal to 1 is always equal to 0. Okay? And why is that? This happens because this is going to be the result of applying the derivation to the product of the function which is constant equal to 1 with itself. Okay? And because of the Leibniz rule, this is the derivation applied to 1 times the value of 1 at the point x, which is 1, plus the value of 1 at the point x, again 1, times the derivation applied to the germ of 1 at x. And so we get that this derivation of 1 is equal to 2 times the same function. So this derivation of the function 1 is equal to 0. Okay? Indeed, we can extend this result to functions that are constant. If we fix now a real number and we consider the result of applying the derivation to the constant function equal to c, this is the derivation of c times the constant function 1, and this is c times the derivation of 1, which is 0. So the derivation, any derivation applied to a constant function is always equal to 0. Okay. Now consider a tangent vector of m at the point x0, and we can consider local coordinates in the neighborhood of x0. So our tangent vector is going to be, in these local coordinates, some linear combination with real coefficients of the coordinate vector fields. Okay, and what happens is that when we apply this tangent vector to a germ of function defined at the point x0, and here we are going to consider f in local coordinates too, it's going to be a1 times the derivative of f with respect to x1 and at the point x0 and so on. Okay? In particular, we have to study the map between the tangent space of m at x and the derivations of the space of germs at x. It is clear that because of this formula, right, this map over here is going to be R linear. Okay, and besides that, it's going to be injective, because if one vector, if the result of apply u to any function is 0, in particular, the result of applying u to x1 has to be equal 0, but that's going to be a1. So all these coefficients are 0, so the unique way in which the derivation induced by u is 0 is if our tangent vector is 0. So this map over here is R linear and injective. But what we need to show now is that it is also surjective, and in this way it is an isomorphism of vector spaces. Okay, in order to do this, what we are going to see is the following. We are going to see that if we have two derivations, okay, if we have let's say d and d prime, that are derivations of the space of germs at the point x0, and these derivations satisfy that, okay, x0, let's consider coordinates for that point, for instance, a1, a2, and so on. And if we have the derivation of xi minus ai, okay, this is the germ of this at the point x0, right? Okay. If we have this equality for all I between 1 and n, of course, then what happens is that these derivations are the same. So we just need to know what the value is for xi minus ai. Okay, but we can consider u as the following vector field. The derivation applied to x1 minus a1 at x0 times the partial with respect to x1 and so on. And it's obvious that the derivation induced by u and d have the same value over the functions, over the germs of the functions xi minus ai. So we just need to show the observation. Okay, let's go with that. Let's see that in order to know what the value of the derivation at a germ is, we just need to know the value at these functions. Okay, so consider now, so what we get in this way is that if we have, so that it is clear, if we have this map, and we get D, and we define U in this way, the image of U is going to be D. So the map is going to be surjective. If we prove the remark, okay, that's what we need. But let's see how we can prove the remark. What we have, let's is that if we consider any C-infinity function, okay, then the value at the point x minus the value at the point x0 can be expressed in the following way, as a derivative between 0 and 1 of the derivative with respect to t of the following function, f of x0 plus t times x minus x0, right? This is just the fundamental theorem of calculus. Okay, yeah. Now we're going to do the calculations. This is going to be the integral, because of the chain rule, of the differential of f with respect to xi at the point x0 plus t times x minus x0. And then we have to multiply by the derivative of the e-coordinate of this expression with respect to t. But this is just xi, here we have a sum, of course, is xi minus the e-coordinate, the I-coordinate of x0, which is ai. And since this expression does not depend at all on t, what we get, this is going to be, and also that the integral is a linear operator, we have that this is the sum from I equal 1 to n of the integral of the partial derivative of f with respect to xi at the point x0 plus t times x minus x0 ddt. This is an integral between 0 and 1, and we have to multiply here by xi minus ai. Okay, the function over here is going to be also a infinity function of x. So let's call it gi. And something that it is simple is that the value of gi at x0 is very, very easy to calculate because this expression is equal to 0 if x is equal to x0. So this function over here is constant. And the integral between 0 and 1 of a constant function is just this constant. So it's going to be the partial derivative of f with respect to xi at the point x0. Okay? And now we want to calculate the derivation, right? So the derivation of the germ of f at the point x0 is going to be equal to the derivation, and here we have the germ of the constant function plus the sum from I equal 1 to n of gi x times x minus ai. Okay, that's now the derivation applied to a constant function is 0. And here, for this part, we can use the Leibniz rule. So it's going to be the sum from I equal 1 to n of gi of x0 times the derivation applied to the function x minus ai. Here is xi, I think, yeah. At a point, at the derivation applied to that germ function plus the sum of the derivation applied to gi times the value of this function at x0, which is always equal to 0 because the I coordinate of x0 is ai. So here we have 0. So we can forget this part, but what happens now is that it's over because it is clear that the value of the derivation at the germ of f depends only on this. And why is that? Because we know what these values are. So we get finally that this is the sum from I equal 1 to n of gi at x0, which is just the partial of f with respect to xi at x0 times the differential, the derivation applied to xi minus ai. And that's it. In order to know the value at germ of f, we just need to know this because this obviously is going to depend on f. So any derivation is completely determined by the value of the derivation on the germs of the functions xi minus ai. And in that way, we already saw that our map from the tangent space of M at x0 to the derivations of the space of germs at x0 is surjective. It was already injective and linear, so it is a linear isomorphism. So let us continue with our program, which is establishing a connection between vector fields and derivations. Okay, we did it for the tangent space at a point. Now we are going to do it for vector fields. We're going to define a derivation of the space of C-infinity maps, where here it's the C-infinity functions. It's just, by definition, the space of C-infinity maps from M to the line, okay? A derivation of this space is a map that is R-linear, this is a definition, and such that for every pair of functions, we have the Leibniz rule. The differential of f times g is ddf times g, plus f times ddg, okay? And a vector field induces a derivation of the space of infinity functions, because how we actually provide the image of a function f at a point x0, we consider the tangent vector defined by the vector field at x0, and then we apply this to the germ of f at x0. This, we can do it for every x0. And in this way, we obtain a C infinity function, and since this tangent vector induces a derivation, then we get that x itself induces a derivation. This is very easy to check out. So every vector field is going to induce a derivation of the space of C infinity functions. And what we want to see now is that this map is indeed a bijection. In other words, it's injective, and every derivation is induced by a vector field. Okay? How can we do this? The most difficult part of this proposition is, of course, proving that this map defined over here is surjective. Okay? So let us consider D, a derivation of the space of C infinity functions, and what we're going to see is that D induces, in a narrow way, derivations that we can call dx of the space of germs at the point x. Okay, how can we do this? The first thing that we are going to notice in order to see that this global derivation induces derivations in the space of germs, okay, is that if we have actually D, a derivation, and we consider two maps, f and g, that are indeed C infinity functions, and the germ of these two functions at x0 is the same, then we have that the derivation applied to f at x0 is equal to the derivation applied to g at x0. We want to see that, okay? This is going to be important in order to see that a derivation of the space of C infinity functions induces derivations in the spaces of germs. Okay, so we can consider H, which is the difference between F and G, right? And what we get is that the germ of H at x0 is equal to the germ of the zero function. Since D is linear, D applied to the zero function is going to be just 0, so it suffices to show that the derivation applied to H is equal to 0 at the point x0. If we prove that, then we get this property, which is going to be very interesting for us. So we have that the germ of H at x0 is equal to the germ of the zero function. Okay, and that implies that there exists an open neighborhood U of x0 such that the restriction of H to U is equal to the zero function. Okay, now we're going to express H as a product of two functions. One of them is going to be itself, and the other one is going to be a C infinity function. that we're going to define now. So there exists alpha as C-infinity function such that alpha is equal to 1 in a neighborhood of x0 okay, and the support of alpha is contained in U. And now we are going to consider here the functions h and h times 1 minus alpha. Okay, so we have x0 some open set U, and what happens is that 1 minus alpha is equal to 0 in the neighborhood of x0, and it's equal to 0 in particular, to 1, sorry, it's going to be equal to 1 outside of U. So outside of U, this is equal to 1, and we have that there is equality of these two functions because 1 minus alpha outside of U is equal to 1. And in U, h is equal to 0. So we have equality too because these two functions are 0 over U. And now we are going to use this result and the Leibniz rule to show that when we apply the derivation to h and we see what value it has at x0, that value is equal to 0. Okay? So we have that d applied to h at x0 is going to be d of h applied to x0 times 1 minus alpha of x0 plus, and here we need h of x0 plus d of 1 minus alpha at the point x0, right? This is just the Leibniz rule. But alpha is equal to 1 at x0. In particular, this is 0, right? And sorry, this is a product, of course. And h is also equal to 0 at the point x0. So this is the sum of 0 and 0, and then 0. And we proved what we wanted, that if we have a germ, we have a function, a C-infinity function, whose germ coincides with the germ of the 0 function, okay, then the derivation applied to this function at the point x0 is equal to 0. As a consequence of that, if we have d, which is a derivation of the space of C-infinity functions, we can define derivations of the spaces of germs. Okay, because how can we do this? Fix a point x0, right, in M, and we want to define the value by the derivation of the germ of f at x0. Okay, f is not necessarily defined in the whole manifold, okay? And obviously we're going to define this as the image of some function by the derivation d. So we globalize it. There exists, okay, there exists a function g which is defined in the whole M, and it is C-infinity, such that the germ of G and the germ of F at x0 are the same. That's very easy. And then we define this derivation at x0 applied to this germ as just the value of the value of d applied to g at the point x0. And by the previous result, by the previous remark, this does not depend on the choice of g, because whatever function g we consider over here, if we consider two different functions, their germs at x0 are the same, so the value of d applied to these functions at x0 is going to be the same. So this defines actually a map from the space of germs to R, and it is immediate to show that it is a derivation. So we get this. But in particular now, we have that given D, a derivation, right? We can define now a vector field, because if we consider now a point x0, this construction gives us a differential of the space of germs at x0. And this space of germs has been identified during this lecture with the tangent space of M at x0. So this is going to be d sub x0 when we consider this derivation as a tangent vector. Right? Okay. And what we have to realize now is that in this way we obtain, let's say, a section of the tangent bundle, but this section is indeed going to be C infinity, right? Because if we consider local coordinates, in local coordinates, we're going to have something like this. And by actually, and these coefficients are just going to be the differential, the result of applying the derivation to functions that are equal to x1, x2, and then xn in the neighborhood of a point. Since those functions are C infinity, then yeah, these functions over here are C infinity. So we get a vector field, which is a C infinity vector field of M, right? And it is obvious by construction that the derivation associated to X is equal to D. So what we prove in this way is that the map from the space of C infinity vector fields to the space of derivations, these maps obviously are linear, and we just prove that it is surjective. And it is easy to show that it is injective. If you have a vector field that provides the zero derivation, is because these coefficients, even in local coordinates, are always equal to 0. So the kernel is the trivial vector subspace. So it's also injective. And so we have an identification of the space of C infinity vector fields with the space of derivations of the space of C infinity functions. And we are going to take profit of this identification in the next lectures. In our next lecture, we are going to define the Lie bracket of two vector fields. The results that we saw in this lecture are going to be plenty useful because they allow to define the Lie bracket without using local coordinates. Okay. Then we are going to introduce another concept, the so-called Lie derivative of a vector field with respect to another one, and see that these two concepts, the Lie derivative and the Lie bracket, coincide. By using this identification between Lie bracket and Lie derivative, we are going to prove that the local flows of two vector fields commute if and only if the vector fields commute. In other words, if and only if the Lie bracket of our two vector fields is equal to 0. Thank you for your attention.